Hello there, and welcome to the Sleep Science series. Tonight, we are going to drift beyond our world, traveling millions of miles through the darkness of space to visit a dusty, rust-colored planet that has captured human imagination for centuries. We are going to Mars, and we are going there with a remarkable robotic explorer called Perseverance. This is a story of curiosity and engineering, of patient science and bold ambition. It is a story about a rover the size of a small car, carrying the dreams of thousands of people who designed it, built it, and sent it on a journey across the solar system. Perseverance landed on Mars on February 18, 2021, touching down in an ancient crater that was once filled with water, perhaps even teeming with life billions of years ago. As you settle into your pillows and let the day fall away, imagine the silence of the Martian surface. Picture the pale butterscotch sky, the rusty ochre ground stretching to distant mountains, the thin atmosphere carrying dust devils that spiral across empty plains. There, alone in that vast quiet landscape, sits Perseverance, quietly working, studying rocks, drilling samples, searching for answers to questions that have haunted humanity since we first looked up at that red dot in our night sky. Did life ever exist beyond Earth? Could Mars, our neighboring world, once have been home to living things? What happened to transform a wet, potentially habitable planet into the cold desert we see today? These are the questions that drive this mission, and tonight, we will explore them together as we drift into sleep. The story of Perseverance is also a story about us, about human beings who look at distant worlds and wonder what secrets they hold. It is a story about the remarkable things we can achieve when we work together toward a common goal. Thousands of engineers, scientists, technicians, and dreamers collaborated to make this mission possible, spending years designing instruments, testing systems, solving problems that had never been solved before. And so tonight, let yourself be carried along on this journey. Feel the rhythm of exploration, the patience of careful science, the wonder of standing vicariously on another world through the cameras and instruments of this incredible machine. There is no need to remember every detail, no need to hold on to specific facts. Simply let the story wash over you like waves on a shore, carrying you gently toward rest. The images that Perseverance sends back to Earth show us a world that is both alien and strangely familiar. We see landscapes that could almost pass for deserts in the American Southwest, yet the sky above them is pink, not blue. We see rocks shaped by wind and water, yet no rain has fallen there for billions of years. We see a world that was once warmer, wetter, more Earth-like, now frozen and quiet under a thin veil of atmosphere. But beneath that silence, Mars still holds its secrets. Locked in ancient rocks, preserved in sediments that settled at the bottom of long-vanished lakes, there may be evidence of a time when Mars was alive with possibility. Perseverance is there to find that evidence, to carefully select and collect samples that might one day return to Earth, where scientists can study them with tools too large and sophisticated to send to Mars. This is not a story of sudden discovery or dramatic revelation. It is a story of patience, of careful observation, of slowly building understanding piece by piece. It is the kind of story that lends itself to quiet contemplation, to the soft rhythm of breathing as you drift towards sleep. So let us begin at the beginning, with a launch into the summer sky, and a journey that would take 7 months to complete. On July 30th, 2020, beneath the bright Florida sun at Cape Canaveral, a rocket stood ready on its launch pad. Inside its protective shell, carefully secured and monitored, sat Perseverance, along with a small helicopter tucked beneath the rover's belly. The launch window for Mars missions opens only once every 26 months when Earth and Mars align favorably in their orbits around the Sun. This was the moment. The countdown reached 0, and the Atlas V rocket ignited with a thunderous roar that rolled across the marshlands surrounding the Space Center. Birds scattered from nearby trees as the rocket lifted slowly at first, then faster, climbing on a pillar of flame and smoke into the summer sky. Within minutes, it had disappeared from sight, carrying Perseverance away from the only planet it would ever call home. The timing of the launch was critical. Mars and Earth are constantly moving in their orbits around the Sun, like runners on different lanes of a track. To send a spacecraft from one to the other requires precise calculation of where Mars will be months into the future. Engineers plot a curved path through space, accounting for the gravitational pull of the Sun, the motion of both planets, and countless other variables. The trajectory is not a straight line but an elegant arc, a Hohmann transfer orbit that balances energy efficiency with travel time. For Perseverance, this journey would take just over 6 months. Inside its protective aeroshell, the rover traveled through the emptiness of interplanetary space, where sunlight is dimmer than on Earth and temperatures plunge far below freezing. There were no windows to look out of, no sense of motion as the spacecraft drifted silently at thousands of miles per hour. Only the steady tick of onboard clocks marked the passage of time as Perseverance crossed the vast distance between worlds. During those months of travel, the mission team on Earth maintained constant vigilance. Engineers monitored the spacecraft's systems, checking that solar panels were generating power, that communications equipment was functioning properly, that nothing had been damaged by the launch or by micrometeorite impacts during the voyage. They performed trajectory correction maneuvers, brief firings of small thrusters that adjusted the spacecraft's path, ensuring it would arrive at exactly the right point in space at exactly the right time. Perseverance itself is a marvel of engineering, a sophisticated robot designed to operate autonomously in one of the harshest environments imaginable. The rover is about 10 feet long, 9 feet wide, and 7 feet tall, roughly the size of a compact car. It weighs just over 2,000 pounds, though on Mars, with its lower gravity, it would feel much lighter. Every component was carefully chosen and tested to withstand the journey through space and the conditions on the Martian surface. The rover's body, called the Rover Equipment Deck, sits atop 6 sturdy wheels, each with its own motor. These wheels are made of aluminum and have curved grousers, like treads, that help grip the rocky Martian terrain. Each wheel is slightly larger than the previous Mars rover Curiosity's wheels, designed to be more resistant to the sharp rocks that caused wear on the earlier mission. The wheels can move independently, allowing the rover to turn in place, climb over obstacles, and navigate difficult terrain. Rising from the rover's body is a tall mast, like a neck and head, standing about 7 feet above the ground. This mast holds cameras and scientific instruments that can look around at the landscape, just as a person might turn their head to survey their surroundings. The rover also has a long robotic arm that can extend out from its body, reaching toward rocks to drill samples or study them with instruments mounted on a turret at the arm's end. Inside the rover's body, protected from the harsh Martian environment, sits the rover's brain, a radiation-hardened computer that controls all its systems, There are also batteries to store electrical power, heaters to keep sensitive electronics warm during the frigid Martian nights, and communication equipment to send data back to Earth and receive new commands from mission controllers. Unlike earlier rovers that relied on solar panels, Perseverance is powered by a radioisotope thermoelectric generator, or RTG. This nuclear battery uses the natural decay of plutonium to generate heat, which is then converted into electricity. The RTG provides a steady, reliable source of power regardless of dust storms or the changing seasons on Mars. It will continue to function for many years, powering the rover's instruments and keeping its electronics warm through countless Martian days and nights. As Perseverance crossed the void between Earth and Mars, the red planet gradually grew larger in the spacecraft's view. What started as a bright dot became a distinct world, its surface features becoming visible, its atmosphere a thin haze around its edges. The date was set for landing, February 18, 2021. After 7 months of travel covering 300 million miles, Perseverance would attempt one of the most challenging feats in space exploration, landing safely on the surface of Mars. The engineers and scientists who had worked on the mission for years prepared for the final, most dangerous phase of the journey. Landing on Mars is notoriously difficult. The planet's thin atmosphere provides some braking from a heat shield and parachute, but not enough to slow a spacecraft to a safe landing speed. Yet that same thin atmosphere creates enough friction to generate tremendous heat during entry. It is a delicate balance, requiring split-second timing and flawless execution. The landing site had been chosen with great care, Jezero Crater, a 28-mile-wide impact crater near the Martian equator. From orbit, scientists had identified what appeared to be an ancient river delta at the western edge of the crater. This delta, they believed, had formed billions of years ago when water flowed into a lake that filled the crater. If Mars had ever harbored life, a place like this, where water once pooled and sediments accumulated, would be an excellent place to search for evidence of it. But Jezero Crater was also dangerous. The terrain was rough, filled with boulders, cliffs, and steep slopes. Previous Mars landers had touched down in relatively flat, safe areas. Perseverance would need to land with unprecedented precision, avoiding hazards and touching down within a relatively small target zone. The mission team had spent years studying orbital images of the crater, mapping potential hazards, and planning the approach. As the spacecraft drew closer to Mars, final preparations began. Systems were checked and double-checked. Commands were uploaded to the spacecraft's computer, programming it for the complex sequence of events that would unfold during entry, descent, and landing. Unlike missions to the Moon or spacecraft in Earth orbit, there would be no opportunity for real-time control. Radio signals take many minutes to travel between Earth and Mars, too long to allow for human intervention during the critical landing sequence. Perseverance would have to land itself, executing pre-programmed commands with split-second precision. The quiet months of interplanetary travel were coming to an end. Soon, Perseverance would wake up, orient itself, and prepare for the most challenging 7 minutes of its existence. In the pre-dawn hours of February 18, 2021, by Earth time, Perseverance approached Mars. The spacecraft had been traveling through space for nearly 200 days, but now everything would happen very quickly. From the moment it touched the top of the Martian atmosphere to the moment its wheels touched the ground would be just 7 minutes, a period mission controllers called 7 minutes of terror. During those 7 minutes, everything had to work perfectly. There was no room for error, no chance for course correction. The spacecraft would plunge through the atmosphere at over 12,000 miles per hour, experiencing temperatures exceeding 2,400 degrees Fahrenheit as friction heated its protective heat shield to white-hot intensity. It would deploy the largest supersonic parachute ever sent to Mars. It would fire retro rockets, lower itself on cables, and touch down gently on the alien surface. All of this would happen automatically, controlled by the rover's onboard computer, while mission controllers on Earth could only watch and wait. The entry phase began when Perseverance hit the top of the Martian atmosphere, about 80 miles above the surface. Immediately, friction began to slow the spacecraft down, but also to heat it up dramatically. The aeroshell, a protective shell surrounding the rover like a closed clamshell, took the brunt of this heating. Its heat shield, made of a special material that chars and ablates away, carried heat away from the spacecraft, protecting the rover inside from the inferno outside. Inside Mission Control at NASA's Jet Propulsion Laboratory in California, hundreds of people watched screens displaying telemetry data streaming back from Mars. But this data was already over 11 minutes old, the time it took radio signals to cross the vast distance between the two planets. Whatever was happening at Mars had already happened. Perseverance was either safely on the surface or had crashed trying. All the team could do was wait for the data to arrive, telling them what had occurred in the past. As Perseverance descended through the thin Martian atmosphere, it was not falling straight down but traveling at an angle, like a skipping stone grazing across water. This angled entry allowed it to cover horizontal distance while losing altitude, guiding it toward Jezero crater. The spacecraft used small thrusters to adjust its attitude, making tiny course corrections based on calculations performed by its onboard computer. At about 7 miles above the surface, traveling at just under 1,000 miles per hour, the spacecraft deployed its parachute. This was not a gentle deployment. The parachute was packed in a mortar-like device and was literally shot out, explosively inflating in less than half a second. The parachute was enormous, 70 feet in diameter, and it immediately caught the thin Martian air, jerking the spacecraft hard as it began to slow its descent. The parachute worked beautifully, but even the largest parachute ever sent to Mars could not slow Perseverance enough for a safe landing. The Martian atmosphere is simply too thin, only about 1% the density of Earth's atmosphere. More systems would need to activate to complete the landing safely. About 20 seconds after parachute deployment, the heat shield separated from the spacecraft and fell away, tumbling toward the Martian surface far below. With the heat shield gone, Perseverance could now see the ground approaching. Cameras and radar began to scan the terrain, measuring altitude and velocity, feeding data to the onboard computer. This is where Perseverance demonstrated a capability that earlier Mars landers had lacked: terrain relative navigation. As the rover descended under its parachute, a special camera took rapid-fire images of the ground below. The onboard computer compared these images to a map stored in its memory, a map created from orbital photographs. Within seconds, the computer figured out exactly where the spacecraft was located and where it was headed. Critically, the computer could see whether the predicted landing site was safe or dangerous. If it was headed toward a boulder field or steep slope, the computer could adjust, directing the spacecraft to fly toward a safer spot nearby. This technology, tested for the first time on Perseverance, would allow the rover to land in much more challenging terrain than previous missions had dared to attempt. At about 6,000 feet above the surface, moving at around 170 miles per hour, the spacecraft jettisoned its back shell and parachute. They fell away, leaving the rover in its descent stage, a rocket-powered platform that now took over control of the landing. 8 retro-rockets ignited, engines firing downward to slow the spacecraft's fall and control its position in 3 dimensions. The descent stage, flying on its rockets, looked remarkably like a science fiction spacecraft. It maneuvered actively, adjusting its thrust to slow the descent to a walking pace while simultaneously moving horizontally to the safest landing spot identified by terrain relative navigation. The computer was making thousands of calculations per second, adjusting engine thrust continuously to account for the unpredictable Martian wind gusts and the rover's changing mass as fuel was consumed. At about 65 feet above the surface, the descent stage initiated the final and most dramatic phase of the landing, the sky crane maneuver. The rover was lowered on 3 long cables, like a giant spider being lowered from its web. The cables unspool at a controlled rate while the descent stage continued to fire its rockets, hovering in place as Perseverance descended beneath it. This sky crane maneuver had been used successfully for the Curiosity rover in 2012, but it was still a white-knuckle moment for the mission team. So many things could go wrong. The cables could tangle, the rover could swing, the descent stage could lose control. But the system worked exactly as designed. Perseverance descended smoothly, its 6 wheels deploying and locking into position as it approached the ground. At 12:55 in the afternoon, Pacific Standard Time on Earth, but already 11 minutes in the past at Mars, Perseverance's wheels touched the Martian surface. Weight sensors detected the touchdown, and immediately the rover sent the signal to the descent stage, "I'm down. Let go." Pyrotechnic devices fired, severing the cables connecting the rover to the descent stage. The descent stage, its job complete, increased its thrust and flew away to crash land a safe distance from the rover, its fuel exhausted, its mission accomplished. Inside Mission Control, telemetry confirmed touchdown. Perseverance, safely on the surface of Mars, ready to begin seeking signs of past life, announced the mission commentator. The room erupted in applause and cheers, people leaping to their feet, hugging each other, tears streaming down many faces. Years of work, years of preparation, years of hope and worry culminated in this moment of triumph. Perseverance had survived the 7 minutes of terror and was safely on Mars. Within minutes, the first images began to arrive. Black and white pictures from hazard avoidance cameras showed the ground immediately around the rover, scattered with small rocks and pebbles. Then came images showing one of the rover's wheels sitting firmly on Martian soil, dust kicked up by the landing slowly settling in the thin air. Each new image was greeted with excitement and relief. The rover looked healthy, its systems functioning normally, its solar-charged batteries already beginning to draw power from the weak Martian sunlight filtering through the dust. Perseverance had arrived at its new home, an ancient crater floor that had not felt the touch of moving water for more than 3 billion years. The rover sat quietly now, beginning its initial system checks. preparing to wake fully and begin its long mission of exploration and discovery. The landing site, later named Octavia E. Butler Landing after the celebrated science fiction author, would be the starting point for a journey of many miles across the crater floor and up into the ancient delta where water once flowed. But for now, in these first moments after landing, Perseverance simply sat and waited, gathering data, charging its batteries, preparing for the work ahead. On Earth, the mission team began the careful process of bringing the rover fully online, checking every system, every sensor, every instrument to ensure that everything had survived the journey and the landing intact. The 7 minutes of terror were over. The mission was just beginning. Perseverance had not landed in a random location. Jezero Crater had been chosen after years of careful study and debate. More than 60 potential landing sites had been considered for the Mars 2020 mission, each evaluated for its scientific promise, its accessibility, and its safety. In November 2018, after extensive review, mission planners made their final selection. Jezero Crater it would be. Jezero, a name derived from a word meaning lake in several Slavic languages, is an impact crater approximately 28 miles in diameter, located just north of the Martian equator. Like most large features on Mars, Jezero was created by a violent asteroid or comet impact billions of years ago. The impact excavated a massive bowl in the Martian crust, throwing debris high into the thin atmosphere where it rained back down to form the crater's raised rim. But what makes Jezero special, what drew scientists to choose it as Perseverance's landing site, is not the crater itself but what happened there long after the impact. Orbital images, particularly those captured by NASA's Mars Reconnaissance Orbiter, revealed something remarkable at the western edge of the crater, a fan-shaped deposit of sedimentary rock, a formation that looks strikingly similar to river deltas on Earth. This delta told a story. Billions of years ago, when Mars was warmer and wetter than it is today, water flowed across the Martian surface. Rivers carved valleys through ancient highlands, carrying sediment downstream. One of these ancient rivers found its way to Jezero Crater, and the water spilled over the crater's rim, flowing down into the basin below. Inside the crater, the water slowed and spread out, forming a lake. As the river water entered this lake, it dropped its sediment load. Heavier particles like sand and gravel settled first, near where the river entered the lake. Finer particles like silt and clay were carried further before settling in deeper water. Over time, perhaps millions of years, these sediments built up layer upon layer, forming the delta we can still see today, frozen in stone, a testament to a time when Mars had rivers and lakes. The delta at Jezero is not a small feature. It extends several miles into the crater, and its sedimentary layers can be seen clearly in orbital images, stacked like pages in a book. Each layer represents a different moment in Martian history, a different flood event, a different season or climate condition. Reading these layers is like reading the pages of that book, learning about the environmental conditions that existed when the sediments were laid down. Scientists estimate that the lake in Jezero Crater was present more than 3.5 billion years ago, during a period called the Noachian Era in Martian geological history. This was a time when Mars had a thicker atmosphere, warmer temperatures, and liquid water stable on its surface. It may have been the most Earth-like period in Martian history, a brief window when conditions might have been suitable for life to emerge. The presence of the delta is important for several reasons. First, deltas on Earth are excellent places to find fossils. Rivers carry organic material from a wide area and deposit it in the quiet waters of lakes or seas, where it can be buried and preserved in sedimentary rock. If life ever existed in the watershed that fed Jazero's ancient lake, evidence of that life might have been transported to the delta and preserved there. Second, the types of rocks found in and around the delta can tell us about the chemistry of the ancient water. Certain minerals form only in the presence of water, and the specific minerals that form depend on the water's pH, its salinity, its temperature. By studying the minerals in the delta rocks, scientists can reconstruct the environmental conditions and assess how suitable those conditions would have been for life. Shortly after Perseverance landed, the mission team used the rover's cameras to capture detailed images of the delta's edge, visible from the landing site several miles away. What they saw excited and intrigued them. The sedimentary layers were clearly visible, and they showed signs of having been deposited by flowing water. But the images also revealed something unexpected: large boulders scattered across the delta's surface, some as large as cars. These boulders did not belong. They were too large to have been carried by the gentle currents of a river flowing into a lake. After careful study, scientists realized what they were seeing: evidence of catastrophic flooding. At some point, perhaps toward the end of Jazero's existence as a lake, massive flood events had occurred, powerful enough to carry enormous boulders tens of miles downstream and deposit them in the delta. This discovery painted a picture of dramatic climate change on Mars. The planet had transitioned from an era of stable rivers and lakes to a period of intense, episodic flooding, and eventually to the cold, dry desert world we see today. What could have caused such a dramatic transformation? The answer likely lies in Mars losing its global magnetic field, which allowed solar wind to strip away much of its atmosphere over hundreds of millions of years. With less atmospheric pressure, liquid water could no longer remain stable on the surface. The climate dried out, rivers ceased to flow, and lakes either evaporated or froze. But before that happened, for a geologically brief but significant period, Jezero crater held a lake. Water lapped at its shores. Sediments settled in its depths. And if life existed anywhere on Mars during that time, this would have been an ideal environment for it. As Perseverance began its exploration of Jezero, the rover first had to cross the crater floor before it could reach the delta. Scientists were surprised to discover that the crater floor was not made of sedimentary rocks as they had expected. Instead, the rocks were igneous, formed from cooling magma. Some were olivine-rich cumulate rocks, created when minerals crystallized and sank to the bottom of a thick magma chamber, perhaps from lava flows that flooded the crater floor long before the lake existed. Even these igneous rocks, however, showed evidence of interaction with water. Chemical analysis revealed carbonate and sulfate minerals, which form when rock is altered by water. This suggested that even after the lake had dried up, groundwater or brief wet periods had continued to modify the rocks, leaving chemical fingerprints that Perseverance could detect billions of years later. The rover also found evidence of more recent processes. Sand ripples, shaped by Martian winds, stretched across the landscape. Small impact craters, some very recent, pockmarked the surface. Dust devils, whirlwinds of airborne dust, occasionally drifted past, visible in the rover's cameras as faint, twisting columns rising into the pink sky. Jezero Crater today is a quiet place. No water flows, no waves lap at ancient shores. The only sound is the whisper of wind carrying dust grains across weathered rocks. But Perseverance was there to listen to the whispers of a much older past, a time when this crater was full of water and possibility. As the rover studied the crater floor, mission scientists planned the journey ahead. The route would take Perseverance several miles westward, climbing gradually up onto the delta itself. There, among the sedimentary layers, among the clays and carbonates that formed in the ancient lake, the rover would search for the ultimate prize, evidence that life, however microbial, however simple, once existed on Mars. The journey would take time. Perseverance could travel at most a few hundred meters on a good day, and there would be many stops along the way to study interesting rocks, to drill samples, to capture images and gather data. But time was something the mission had plenty of. The rover's plutonium power source would keep it running for years, perhaps more than a decade if all went well. And so Perseverance set out across Jezero Crater, following in the footsteps of ancient waters, searching for clues to one of humanity's deepest questions: are we alone, or has life emerged elsewhere in our solar system? To understand what Perseverance sees and studies on Mars, we need to understand the remarkable collection of scientific instruments the rover carries. Unlike earlier Mars rovers that were primarily geological surveyors, Perseverance was designed specifically for astrobiology, the search for signs of ancient life. Its instrument suite reflects this mission, combining tools that can analyze rock chemistry at a microscopic scale with cameras that can capture the Martian landscape in stunning detail. Starting at the top, literally, Perseverance's mast stands 7 feet above the ground, giving the rover a human-like vantage point from which to survey its surroundings. Mounted on this mast are several camera systems and a powerful instrument called SuperCam. SuperCam is one of Perseverance's most versatile tools. It combines a high-powered laser, a telescope, cameras, and 3 different spectrometers in a single package. Here's how it works. SuperCam can fire its laser at a rock up to 20 feet away. The laser pulse vaporizes a tiny amount of rock, creating a flash of plasma, a superheated gas that glows briefly. SuperCam's spectrometers analyze the light from this plasma, and because different elements emit light at different wavelengths, the spectrometers can determine what chemical elements are present in the rock. This technique, called laser-induced breakdown spectroscopy, allows Perseverance to analyze rocks from a distance, without having to drive up to them and use contact instruments. SuperCam can zap dozens of rocks in a single day, rapidly surveying an area to identify the most interesting targets for closer study. The instrument can even analyze the composition of dust particles suspended in the Martian atmosphere, helping scientists understand what minerals are being weathered and blown around by Martian winds. Also on the mast is MastCam Z, a pair of cameras that work together like human eyes to create 3-dimensional, stereoscopic images. Each camera has a zoom lens, allowing mission operators to examine distant features in detail or take wide-angle panoramas of the landscape. MastCam Z captures images in multiple color filters, revealing details invisible to the human eye, such as variations in mineral composition that show up differently under different wavelengths of light. These cameras serve a practical purpose beyond science. They help the mission team navigate, identifying obstacles, planning routes, and selecting interesting rocks for closer examination. But they also serve to bring Mars to Earth, allowing anyone with an internet connection to see what Perseverance sees, to explore vicariously a landscape that no human has ever walked. At the end of Perseverance's robotic arm, held like tools in a hand, is a collection of instruments known as the turret. The arm itself is 7 feet long and has multiple joints, allowing it to position instruments precisely on rock surfaces or maneuver them into confined spaces. The turret at the arm's end looks somewhat like a human hand, though instead of fingers, it has scientific instruments and a drill. One of the most important instruments on the turret is called Sherlock, which stands for Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. The name is a playful nod to Sherlock Holmes, and indeed, Sherlock is a detective of sorts, searching for clues about Mars' past habitability. Sherlock uses ultraviolet light and 2 types of spectroscopy to analyze rocks at a very fine scale. When ultraviolet light shines on certain organic molecules, they fluoresce, glowing faintly at visible wavelengths. Sherlock can detect this fluorescence, potentially identifying organic compounds preserved in Martian rocks. The instrument also uses Raman spectroscopy, which reveals information about the molecular structure of minerals, helping scientists understand how rocks formed and whether they were altered by water. Working alongside Sherlock is an instrument called PIXL, the Planetary Instrument for X-ray Lithochemistry. PIXL uses X-rays to determine the elemental composition of rocks with incredible precision. It can create detailed maps showing the distribution of different elements across a rock surface, revealing variations too small to see with cameras. These maps help scientists understand how minerals are arranged in rocks, which in turn provides clues about how the rocks formed and what environmental conditions existed at the time. Both Sherlock and PIXL can analyze rocks in their natural state, but Perseverance also has the ability to look beneath a rock's weathered surface. The turret includes an abrasion tool, essentially a rotating grinding wheel that can scrape away the outer layer of a rock, revealing fresh, unweathered material underneath. This is important because Martian rocks have been sitting on the surface for billions of years, exposed to harsh ultraviolet radiation, oxidizing compounds, and wind-blown dust. The interior of a rock is more likely to preserve original minerals and any ancient biosignatures that might be present. The turret also holds the rover's drill, a powerful tool capable of drilling into solid rock to collect cylindrical cores about the width of a pencil and up to 6 inches long. This drill is at the heart of Perseverance's sample collection mission, a mission we will explore in more detail later. For now, it is enough to know that the drill can penetrate igneous rocks, sedimentary rocks, and even relatively hard sandstones, extracting intact cores that preserve the rock's internal structure and composition. Lower on the rover's body are cameras designed for navigation and hazard avoidance. Perseverance has multiple sets of these cameras, positioned to look in different directions. They capture black and white images that help the rover's autonomous navigation system identify safe paths through rocky terrain. These cameras work constantly as the rover drives, allowing it to detect obstacles and adjust its path in real time without waiting for commands from Earth. Inside the rover's body, protected from the Martian environment, is an instrument called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. MOXIE is not a science instrument in the traditional sense. Instead, It is a technology demonstration, testing a process that could one day support human exploration of Mars. We will discuss MOXIE's achievements in detail later in our story. Perseverance also carries an instrument called META, the Mars Environmental Dynamics Analyzer. META is essentially a weather station, measuring atmospheric pressure, temperature, wind speed and direction, humidity, and the amount of dust in the air. These measurements help scientists understand Mars' weather patterns and seasonal changes, information that will be crucial for planning future missions, especially those involving human explorers who will need to know what environmental conditions to expect. Finally, Perseverance has something that earlier Mars rovers lacked: microphones. For the first time in history, we can hear Mars. One microphone is part of SuperCam, capturing the sound of the laser hitting rocks. Another is designed to record the general sounds of the Martian environment. The sounds they capture are eerie and otherworldly: the whisper of wind, the crunch of rover wheels on gravel, the distinctive crackling of the laser vaporizing rock, even the low hum of the rover's internal systems. These recordings are more than just curiosities. Sound travels differently through Mars' thin atmosphere than through Earth's thicker air. By analyzing how sounds propagate, scientists can learn about atmospheric properties. The microphones have also captured surprising sounds, like the whoosh of dust devils passing nearby and the clatter of small rocks struck by the rover's wheels. Together, these instruments give Perseverance extraordinary capabilities. The rover can survey its surroundings from a distance, identifying rocks of interest. It can approach those rocks, study them with contact instruments that reveal their chemistry and mineralogy at microscopic scales. It can grind away weathered surfaces to look at fresh rock underneath. And crucially, it can drill cores from the most scientifically valuable rocks, preserving them for eventual return to Earth. This combination of remote sensing and detailed contact science allows Perseverance to be far more selective than earlier missions. Instead of analyzing every rock it encounters, the rover can be strategic, choosing the samples most likely to answer important questions about Mars' history and potential for past life. The instruments work together like a team of scientists, each contributing its expertise. SuperCam scouts ahead, identifying promising targets. MastCam-Z provides context and documentation. The arm delivers Sherlock and PIXL to rock surfaces for detailed analysis. The drill extracts cores. META monitors environmental conditions that might affect measurements. The cameras and microphones record everything, creating a comprehensive archive of the mission. As you drift towards sleep, imagine Perseverance at work. The rover sits motionless on the Martian surface, its robotic arm extended toward a rust-colored rock. SuperCam's laser fires, a brief flash invisible to human eyes but captured by the instrument's sensors. The arm moves closer, and Sherlock's ultraviolet light bathes the rock surface, searching for the faint glow of organic molecules. Data streams back to Earth, traveling for 11 minutes across the vast emptiness of interplanetary space, arriving at an antenna on Earth where scientists eagerly await the results. This is patient work, methodical work, the kind of careful science that builds understanding slowly, one measurement at a time. It is the perfect subject for these quiet moments before sleep, a reminder that discovery often comes not in sudden flashes of insight but through accumulation of evidence, through careful observation, through taking the time to look closely at the world, or in this case, at another world entirely. At the heart of Perseverance's mission is an unprecedented task: collecting samples of Martian rock and soil and preparing them for eventual return to Earth. This is not just about drilling rocks. It is about establishing humanity's first sample depot on another planet, a cache of carefully chosen specimens that might one day make the long journey back to our world for analysis in laboratories here. Tucked inside Perseverance's belly, protected from the harsh Martian environment, is the sample caching system, one of the most complex mechanisms ever sent to another planet. This system includes 43 sample tubes, each made of titanium, each about as long as a ballpoint pen and sealed with pristine hermetic seals. 38 of these tubes are designed to hold samples of rock or soil. 5 are witness tubes, preloaded with materials that can capture any contamination from Earth, allowing scientists to distinguish between Martian material and anything accidentally brought from our planet. Each sample tube weighs less than 2 ounces, yet engineering them was a monumental challenge. They had to be strong enough to survive the journey to Mars, the drilling and caching process, and eventually the journey back to Earth. They had to be sealed so tightly that no Martian material could leak out and no Earth atmosphere could leak in. They had to be cleaner than any spacecraft hardware ever launched, because scientists need to be confident that any organic molecules found in the samples are truly Martian, not contamination from Earth. Achieving this level of cleanliness required extraordinary measures. The tubes and all the caching system's components were assembled in ultra-clean rooms where air is filtered to remove even the tiniest particles. Technicians wore full-body suits and worked under strict protocols. Every surface was cleaned repeatedly with special solvents. The tubes were baked at high temperatures to drive off any trace organic molecules. Even the lubricants used in the caching system's moving parts were specially selected to avoid contamination. The process of collecting a sample begins with identifying a promising rock, usually after weeks of study. The mission team examines images from orbit and from the rover's cameras. They analyze data from SuperCam and other remote sensing instruments. They discuss and debate, weighing the scientific merits of different options. Eventually, they select a target, and Perseverance drives to it, positioning itself carefully. If the rock has a weathered surface, the rover first uses its abrasion tool to grind away the outer layer, creating a circular patch of fresh rock about 2 inches across. This abraded patch is then studied intensively with Sherlock and PIXL, instruments that can reveal the rock's composition in detail. Only if these instruments confirm that the rock is scientifically valuable does the team proceed with drilling. Drilling on Mars is not like drilling on Earth. The rover cannot lean its full weight into the drill to apply pressure. Instead, the drilling system uses a percussive hammering action, pounding the drill bit downward while simultaneously rotating it. The drill bit is hollow, allowing it to cut a cylindrical core of rock while leaving the core intact inside the bit. As the drill works, sensors monitor the process, measuring the resistance of the rock, the temperature of the drill, the vibrations transmitted through the system. If something goes wrong, if the drill encounters a void in the rock or if the rock is too hard, the system can detect it and abort the drilling before damaging the equipment. The entire process is automated but carefully monitored by engineers on Earth, who can intervene if necessary, though with the time delay for radio signals, any intervention must be planned well in advance. Once the drilling is complete, The core, still inside the drill bit, is carefully extracted from the rock. The robotic arm lifts the drill straight up, pulling the core free. Inside the rover's belly, a small robotic arm, working with exquisite precision, takes the drill bit from the larger robotic arm and maneuvers it to a processing station. There, the core is gently pushed out of the drill bit and into one of the waiting sample tubes. Cameras capture close-up images of the core, documenting its appearance, measuring its length, checking for any cracks or issues. If the core looks good, a hermetic seal is attached to the tube, and the tube is sealed permanently, locking the sample inside with a tiny amount of Martian atmosphere. The sealed tube is then stored inside the rover's belly, held in a carousel that can rotate to present any tube when needed. Detailed records are kept of which tube contains which sample, where the sample was collected, what instruments analyzed the source rock, and all the environmental conditions at the time of collection. As of late 2023, Perseverance had collected more than 24 samples, each one a piece of Mars' geological history. Some are igneous rocks that formed from cooling magma. Others are sedimentary rocks laid down in water. There are samples rich in carbonate minerals, samples containing sulfates, samples from the crater floor and samples from the ancient delta. Each sample tells a story. Some contain fine-grained sediments that settled in calm water, perhaps in the ancient lake that filled Jezero crater. Others show evidence of alteration by water, with minerals that form only in wet conditions. A few contain organic molecules, carbon-containing compounds that, while not direct evidence of life, show that the chemistry of Mars included the building blocks from which life on Earth is made. One particularly intriguing sample, collected from a rock informally named Chiava Falls, shows features that have excited scientists. This rock contains organic molecules alongside structures that could be fossilized microbes or could be geological features that merely look biological. Without bringing the sample to Earth for detailed analysis with sophisticated laboratory instruments, scientists cannot be certain. This ambiguity is precisely why sample return is so important. But Perseverance is not keeping all these samples aboard. In late 2022 and early 2023, the rover created humanity's first sample depot on another planet, carefully placing 10 sample tubes on the Martian surface at a location called Three Forks. This depot serves as a backup. If, in the future, a mission comes to collect samples from Mars and Perseverance is unable to hand off its samples directly, the depot can be retrieved instead. Creating the depot required exquisite precision. Each tube had to be placed at a specific location, carefully documented so future missions could find them even if dust had partially covered them. After depositing each tube, Perseverance photographed it from multiple angles, then drove away and photographed the depot site from a distance, creating a detailed map. The tubes were placed in a complex zigzag pattern, spaced far enough apart that a future rover or lander could access any individual tube without disturbing others. The entire depot covers an area about the size of a parking lot, marked by the small titanium tubes lying on the reddish Martian soil, glinting faintly in the sunlight. Looking at images of the depot is surreal. There, on the surface of Mars, lie these small human-made objects, each containing a piece of another world, waiting patiently for a future mission that will retrieve them and carry them across the solar system back to Earth. It is a time capsule of sorts, though instead of preserving the past for future humans, It preserves Martian geology for current human study. The plan for Mars sample return is ambitious and complex. Sometime in the late 2020s or early 2030s, if all goes according to plan, another mission will launch from Earth. This mission will include a lander and a small rocket called the Mars Ascent Vehicle. The lander will touch down near Perseverance or near the sample depot. If Perseverance is still functioning, it will transfer its samples to a robotic arm on the lander, which will place them in a container on the Mars Ascent Vehicle. If Perseverance has ceased functioning, small helicopters or a fetch rover will retrieve tubes from the depot. Once the samples are secured, the Mars Ascent Vehicle will blast off from the Martian surface, the first rocket launch from another planet. In orbit around Mars, another spacecraft will be waiting. This orbiter will rendezvous with the container carrying the samples, capture it, seal it inside a highly secure containment system, and then fire its engines to leave Mars orbit and begin the long journey back to Earth. After months of travel, the spacecraft will approach Earth and release a landing capsule containing the samples. The capsule will streak through Earth's atmosphere at tremendous speed, slowed by heat shields and parachutes, finally touching down in a remote location, perhaps a desert, where recovery teams will be waiting. The samples will then be transported to a special facility designed to handle extraterrestrial material safely, a place where scientists from around the world can study them using every analytical technique available. This is the vision, the long arc of the mission that began with Perseverance's launch in 2020. It is a vision that spans decades, that requires the coordination of multiple space agencies, that pushes the boundaries of what is technically possible. It is also a vision that might answer one of humanity's oldest questions: are we alone? As you lie here in the quiet of your room, on a planet rich with life, imagine those sample tubes on Mars. They sit motionless on the Martian surface or ride safely inside Perseverance's belly, waiting. Inside them are fragments of rock billions of years old, formed in conditions we can only reconstruct from the evidence they preserve. Perhaps those rocks hold secrets, traces of ancient life, fossilized microbes from a time when Mars was a warmer, wetter world. Or perhaps they will show that Mars, despite its ancient lakes and rivers, never developed life at all. That answer, too, would be profound, teaching us something fundamental about how life arises, how common or rare it might be in the universe. Either way, the samples wait, patient as stone can be, for the day when human hands will finally hold pieces of Mars and see what stories they tell. Tucked inside Perseverance's body, roughly the size of a car battery, sits an instrument that is less about science and more about the future. It is called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment, and its job is to do something that sounds simple but is actually quite remarkable: take Martian air and turn it into oxygen. The atmosphere of Mars is very different from Earth's. Our atmosphere is mostly nitrogen and oxygen, the oxygen being what we breathe and what sustains the vast majority of life on our planet. Mars' atmosphere, by contrast, is 95% carbon dioxide, with only trace amounts of nitrogen, argon, and other gases. It is also extremely thin, with a surface pressure less than 1% of Earth's atmospheric pressure. You cannot breathe Martian air, not only because it lacks oxygen but because it is so thin that it would not provide enough gas to sustain breathing even if it were all oxygen. For future human explorers traveling to Mars, this poses a problem. Astronauts would need oxygen to breathe, of course, but they would also need far larger quantities of oxygen for another purpose: rocket fuel. Launching a rocket requires enormous amounts of propellant, and the most efficient rocket propellants combine fuel with an oxidizer, typically liquid oxygen. To return 4 astronauts from the Martian surface to orbit would require approximately 25 tons of liquid oxygen. Bringing that much oxygen from Earth would itself require enormous amounts of fuel just to launch it. The rocket that carried it would be so large, so heavy, that the mission might not be feasible at all. But what if astronauts could make oxygen on Mars, using resources already available there? This is the concept behind MOXIE. If we can demonstrate that we can produce oxygen from the Martian atmosphere, future missions could carry much smaller, lighter systems to Mars, systems that would produce all the oxygen needed for both breathing and rocket propellant. This would make human missions to Mars far more practical and far less expensive. The process MOXIE uses is called solid oxide electrolysis. It works like this: Martian air is drawn into the instrument through a filter that removes dust. The carbon dioxide in the air is compressed slightly, then heated to about 800 degrees Celsius, hot enough to make metal glow red. At these high temperatures, the carbon dioxide molecules are separated into carbon monoxide and oxygen ions. The oxygen ions pass through a special ceramic material that conducts oxygen ions but not other molecules. On the other side, the oxygen ions combine to form molecular oxygen, the same kind we breathe. The process requires electricity, which MOXIE draws from Perseverance's nuclear power source, and it produces oxygen at a modest rate, about 6 grams per hour when running, roughly the rate at which a large tree produces oxygen on Earth through photosynthesis. That is not much, certainly not enough to support a human mission. But MOXIE is just a demonstration, a proof of concept. A full-scale system for a human mission would be hundreds of times larger, able to produce tons of oxygen over the months before astronauts arrived. MOXIE first ran on April 20, 2021, about 2 months after Perseverance landed on Mars. Mission controllers activated the instrument and waited nervously as it went through its startup sequence. The system had to heat up, which took time. Then it had to begin processing Martian air, separating oxygen from carbon dioxide. Sensors monitored every step, and data streamed back to Earth. The instrument worked beautifully. In its first run, MOXIE produced about 5 grams of oxygen, roughly enough to keep an astronaut alive for 10 minutes. The oxygen was analyzed to check its purity, and preliminary measurements showed it was nearly 100% pure. Mission controllers allowed themselves a moment of celebration. This was the first time humanity had manufactured a useful resource on another planet, the first demonstration of what scientists call in situ resource utilization, using local materials rather than bringing everything from Earth. Over the following months and years, MOXIE ran dozens more times, operating in different seasons and times of day to test how well it worked under varying conditions. Mars has seasons, though they are quite different from Earth's because Mars' orbit is more elliptical. The atmospheric density changes throughout the Martian year, and MOXIE was designed to function across this range of conditions. The instrument proved remarkably reliable. By the time the experiment concluded in 2023, MOXIE had run 16 times, producing a total of 122 grams of oxygen. That is about 4 ounces, enough to keep a small dog breathing for 10 hours. Again, it is not much, but the point was to demonstrate that the technology works, that oxygen can be reliably produced from Martian carbon dioxide using equipment that can be sent to Mars on future missions. The engineers and scientists who designed MOXIE learned valuable lessons from the experiment. They learned how the instrument performs in the actual Martian environment, with its dust, its temperature extremes, its radiation. They identified ways to make future versions more efficient, lighter, more robust. Most importantly, they proved that the concept is sound, that astronauts traveling to Mars can indeed plan to make their own oxygen rather than bringing it all from Earth. Imagine a future mission, perhaps in the 2030s or 2040s, when the first humans prepare to travel to Mars. Before they launch, an unmanned cargo ship would go ahead, landing on Mars and deploying a scaled-up oxygen production system, perhaps 100 times larger than MOXIE. This system would run for months, filling tanks with liquid oxygen. By the time the astronauts arrive, the oxygen they need for the return journey would already be waiting for them, produced from the Martian atmosphere, stored and ready to use. This kind of capability, using local resources, is essential for sustainable exploration beyond Earth. The Moon has resources too: water ice and permanently shadowed craters, minerals in the regolith that might be processed for oxygen and metals. Asteroids contain metals and water. If humans are to become a spacefaring civilization, we will need to learn to use what we find rather than carrying everything from Earth. MOXIE represents a first step, a small golden box aboard a rover on Mars, quietly proving that this future is possible. As you drift towards sleep, think of that instrument, sitting silent now, its work complete, but having demonstrated something profound, that we can use the resources of other worlds, that the challenges of space exploration can be met with ingenuity and determination. The oxygen MOXIE produced was not saved. It was vented back into the Martian atmosphere immediately after being measured. But the knowledge gained from the experiment, the confidence that the technology works, that is something we keep. That is something we can build on as we plan for the journeys ahead. Beneath Perseverance's belly, protected by a shield during the 7-month journey to Mars, rode a small helicopter named Ingenuity. This was not a science instrument. It was a technology demonstration, an experiment to see if powered, controlled flight was even possible in the thin Martian atmosphere. Nobody knew for certain if it would work. But on April 19, 2021, Ingenuity rose into the Martian sky and became the first aircraft to achieve powered flight on another planet. Ingenuity, affectionately nicknamed Ginny by the mission team, is tiny compared to helicopters on Earth. It stands just 19 inches tall and weighs only 4 pounds. Most of that weight is battery, necessary to power the helicopter during flight. The rest is a small computer for navigation and control, 2 cameras, and the most distinctive feature, 2 sets of rotor blades, each about 4 feet across, mounted one above the other and rotating in opposite directions. Those rotor blades have to spin extraordinarily fast. On Earth, a helicopter's rotors might turn at about 400 to 500 revolutions per minute. Ingenuity's rotors spin at over 2,400 revolutions per minute in Martian conditions. They have to spin this fast because Mars' atmosphere is so thin, roughly 1% the density of Earth's atmosphere at sea level. There are simply fewer air molecules for the rotors to push against. so they must spin faster to generate enough lift. The challenges of flying on Mars are numerous. The thin atmosphere makes generating lift difficult, but it also means there is less air resistance, so the helicopter can potentially move very quickly once airborne. The lower gravity, about 38% of Earth's, helps somewhat, but not enough to compensate for the thin air. And then there is the cold. Martian nights are brutally cold, temperatures dropping to -130 degrees Fahrenheit or lower. Ingenuity's batteries and electronics could not survive such temperatures without protection. To stay warm, Ingenuity has heaters powered by its solar panel during the day and by its battery at night. On particularly cold nights, the helicopter can use more energy keeping warm than it uses for an entire flight. This meant that Ingenuity had to be very energy efficient, squeezing every bit of performance from its small battery while reserving enough power to survive the cold nights. The plan, initially, was for Ingenuity to make 5 test flights over 30 Martian days, demonstrating that flight was possible and collecting data about how the helicopter performed in real Martian conditions. Each flight would be progressively more ambitious, testing different capabilities, pushing the boundaries of what the little helicopter could do. Perseverance deployed Ingenuity on April 3, 2021, gently lowering it to the Martian surface and then driving away to a safe distance. For the first few days, Ingenuity sat alone on the surface, charging its batteries from its solar panel, running systems checks, communicating with Perseverance, which served as a radio relay to Earth. All the while, mission controllers monitored the helicopter's health, making sure it was surviving the cold nights, that its systems were functioning properly. On April 19th, the conditions were right. The wind was calm, the solar illumination good, all systems green. Mission controllers sent the command to fly, though with the time delay for radio signals, the flight would be over before they knew it had begun. Ingenuity was entirely on its own, following pre-programmed instructions, using its onboard computer to control its flight moment by moment. At 3:34 in the morning Pacific time on Earth, but early afternoon on Mars, Ingenuity's rotors began to spin, accelerating to flight speed. The helicopter bounced slightly on its spindly landing legs, then lifted smoothly into the thin air. It rose straight up to a height of 10 feet, hovered there for 30 seconds, then descended and landed gently. The entire flight lasted just 39 seconds. But in those 39 seconds, history was made. Ingenuity had become the first powered, controlled aircraft to fly on another planet, a genuine Wright brothers moment more than 100 years after Wilbur and Orville Wright achieved the first powered flight on Earth. In recognition of this achievement, NASA named Ingenuity's takeoff and landing spot Wright Brothers Field, and the International Civil Aviation Organization gave it an official airport code, JZRO, for Jezero Crater. Ingenuity even carried a small piece of fabric from the original Wright Flyer's wing, a fragment of history transported to Mars to witness a new chapter in aviation history. The parallel was not lost on anyone. Just as the Wright brothers' flights at Kitty Hawk opened the door to aviation on Earth, Ingenuity opened the door to aerial exploration of other worlds. The second flight, 2 days later, went higher and lasted longer. Ingenuity climbed to 16 feet, hovered, moved laterally a short distance, then returned to its takeoff spot. The third flight was even more ambitious, traveling 50 meters downrange at a speed of about 4 miles per hour before returning. With each flight, confidence grew. The helicopter was performing better than expected, its systems working flawlessly in a harsh Martian environment. After the initial 5 test flights proved successful, NASA made a decision: extend Ingenuity's mission, transitioning from a technology demonstration to an operations demonstration. Instead of being retired, Ingenuity would continue flying, serving as an aerial scout for Perseverance, exploring areas the rover planned to visit, identifying routes and interesting features from above. This decision led to nearly 3 years of additional flights. Ingenuity explored terrain ahead of Perseverance, captured stunning aerial images of the Martian landscape, and repeatedly proved its value as a scouting tool. The helicopter flew farther and faster than anyone had initially thought possible, sometimes covering hundreds of meters in a single flight. By its 25th flight, Ingenuity had traveled more than 3 miles total, spending over 40 minutes in the air across all its flights. It had scouted routes through boulder fields, examined the ancient river delta from above, and photographed Perseverance's landing hardware, helping engineers understand how the entry, descent, and landing system had performed. Some flights were especially memorable. On one flight, Ingenuity flew over and photographed the remnants of Perseverance's parachute and back shell, hardware that had been jettisoned during the landing and had crashed to the surface several miles from the rover. These images provided valuable information for future mission planning, showing how well the hardware had survived the landing and where it had come to rest. The helicopter also helped Perseverance navigate complex terrain. On several occasions, aerial images from Ingenuity revealed hazards or features not visible from the ground, allowing mission planners to adjust Perseverance's route or select better sampling locations. The view from above provided context that was impossible to get from the rover's cameras, which, though elevated on the mast, were still at ground level. Ingenuity's flights were not always easy. As the helicopter moved into more rugged terrain, navigating became more challenging. The navigation system relied on identifying features and images taken during flight and using those features to track the helicopter's position. Over smooth sand, features were scarce, and Ingenuity had trouble tracking its position accurately. Over rough, rocky terrain, there were too many features, confusing the navigation system. Software updates sent from Earth helped address these issues, improving the helicopter's ability to navigate varied terrain. These updates were possible because Ingenuity's computer could be reprogrammed remotely, allowing engineers to fix bugs and add new capabilities as they learned more about how the helicopter performed on Mars. Eventually, after 72 flights covering 10.5 miles over nearly 3 years, Ingenuity's remarkable journey came to an end. On January 18, 2024, during what would be its final flight, one or more of Ingenuity's rotor blades were damaged, likely by striking the ground during landing. The helicopter could no longer fly safely. Engineers on Earth assessed the damage through images sent back by Perseverance and by Ingenuity's own cameras. The damage was severe enough that flight was no longer possible. And so, after far exceeding its design life and completing more than 14 times its planned number of flights, Ingenuity was retired, though it continued to communicate with Perseverance, sending weather data and serving as a test platform for radio equipment. The legacy of Ingenuity extends far beyond its 72 flights. It proved that rotorcraft can operate on other worlds, opening new possibilities for exploration. NASA is already planning a much larger helicopter called Dragonfly, which will explore Saturn's moon Titan in the 2030s. Dragonfly will be the size of a car, with 8 rotors, capable of flying for many miles and carrying sophisticated scientific instruments. Future Mars missions might include helicopters as standard equipment, not just for scouting but for transporting small payloads, collecting samples from inaccessible locations, or exploring areas too dangerous for rovers. Ingenuity showed the way, a tiny helicopter that could, against all odds, take to the skies above another world. As you lie here drifting towards sleep, imagine that first flight. Picture Ingenuity sitting on the Martian surface, its rotors a blur of motion, dust swirling as it lifts off. See it rise into the pale butterscotch sky, hovering there, a small human-made machine floating in alien air, sunlight glinting off its solar panel. It is a moment of grace and triumph, a reminder that exploration is not just about going to new places but about learning new ways to explore. And then imagine Ingenuity after its final flight, sitting motionless now on the Martian surface, its mission complete, its blades damaged but its place in history secure. There it will remain, perhaps for millions of years, a monument to ingenuity in every sense of the word, to human curiosity and determination, to the spirit that looks at impossible challenges and says, "Let us see if we can find a way." Perseverance does not operate continuously. Instead, its days follow a rhythm dictated by the rotation of Mars, by the availability of power, and by the complex dance of communication with Earth. Understanding this daily rhythm helps us appreciate the patience required for Mars exploration, the careful planning that goes into every action, the long stretches of time spent gathering data and sending it across the solar system. A Martian day, called a sol, is about 24 hours and 40 minutes long, slightly longer than an Earth day. Mission controllers working with Perseverance must adjust to this Martian time, staying synchronized with the rover's day-night cycle. For people on Earth, this means their working hours slowly drift compared to normal Earth time, advancing 40 minutes each day. After a few weeks, they might find themselves working through what would normally be nighttime, their schedules completely inverted from local time. Perseverance wakes each Martian morning as sunlight begins to fall on its solar panel, or more accurately, as the rover's internal clock triggers its wake-up sequence. The rover is powered by a nuclear battery that provides constant electricity regardless of day or night, but it still follows a daily routine, conserving power during the cold nights and becoming more active during the day. The rover begins by checking its systems, battery charge, temperature sensors, the status of its various instruments and actuators. It communicates with Earth through one of several Mars orbiters that serve as relay satellites. The rover sends up its status report, and ground controllers on Earth review it, checking for any anomalies or issues that need attention. Then the real work begins. If Perseverance has been commanded to drive, it might spend several hours traversing the Martian landscape, covering perhaps 100 meters or more, its cameras scanning ahead for obstacles, its wheels gripping the rocky ground. Driving requires concentration and care. The rover's autonomous navigation system can detect and avoid small obstacles, but it relies on good visibility and cannot anticipate hazards too far ahead. If the plan for the sol includes scientific observations, Perseverance will position itself carefully, perhaps parking on level ground with a good view of a target rock. The robotic arm will extend, positioning instruments precisely on the rock's surface. Data will flow from sensors, filling the rover's computer memory with measurements and images. All of this happens slowly. The arm moves gradually, taking minutes to extend fully and position an instrument. Measurements take time as instruments scan across a rock surface or collect spectra at multiple wavelengths. The rover is patient, methodical, taking care to do everything correctly because there is no opportunity to go back and repeat a measurement if something goes wrong. Communication between Earth and Mars is constrained by distance and orbital mechanics. Radio signals, traveling at the speed of light, take between 4 and 24 minutes to cross the gap between the two planets, depending on where they are in their orbits. This means that Perseverance cannot be controlled in real time like a remote control car. By the time controllers on Earth see what the rover is seeing, whatever they see happened many minutes ago. If they send a command to stop or turn, that command will take minutes to arrive at Mars. Instead, Perseverance operates autonomously most of the time, following detailed instructions uploaded from Earth. Mission planners spend each sol planning the next sol's activities, crafting command sequences that tell the rover exactly what to do and when to do it. These plans must anticipate problems, include contingencies, and account for the limited resources of power and data storage available to the rover. The planning process involves dozens of people, scientists who decide what to study, engineers who ensure commands are safe and feasible, system specialists who monitor subsystems like thermal control and power management. They meet in a series of planning sessions, each group contributing their expertise, debating options, making compromises. The final command sequence is assembled, checked again, and then uploaded to the rover through the Deep Space Network, a system of large radio antennas located in California, Spain, and Australia. These antennas, each as large as a house, point at Mars for hours at a time, capturing the faint radio signals from Perseverance. The rover's transmitter produces only a few watts of power, no more than a dim light bulb, and that signal has to travel millions of miles through space. By the time it reaches Earth, it is extraordinarily weak, detectable only by these enormous, sensitive antennas. The rover can communicate directly with Earth, but more often it sends its data to one of several spacecraft orbiting Mars. These orbiters have large antennas and powerful transmitters, and they pass over Perseverance's location several times each sol. When an orbiter is overhead, Perseverance points its antenna upward and transmits data as quickly as it can during the few minutes the orbiter is in range. The orbiter stores this data, then relays it to Earth when it has a good view of our planet. This relay system allows Perseverance to send far more data than it could by communicating directly with Earth. Images, scientific measurements, engineering telemetry, it all flows up to the orbiters and then down to Earth, where mission controllers eagerly await each new batch of data. Power management is a constant consideration. Although Perseverance's nuclear power source is reliable, the rover still has a limited power budget. Running all instruments simultaneously would drain the battery. Running heaters to keep electronics warm at night consumes significant energy. Driving uses power, especially when climbing slopes or navigating rough terrain. Mission planners must balance these demands, prioritizing the most important activities, ensuring the rover never runs out of power. The rover's computer must also manage data storage. Every image, every spectrum, every measurement consumes memory. With limited storage capacity, Perseverance must be selective about what data to keep and what to discard. High-priority science data is preserved carefully, compressed to save space, and queued for transmission to Earth. Lower-priority data might be kept temporarily, then overwritten when new data needs to be stored. Sometimes, things do not go as planned. A wheel might slip on loose sand, causing the rover to travel less far than expected. An instrument might encounter an error and need to retry a measurement. Dust storms, though less severe at Jezero crater than in some other regions of Mars, can reduce visibility and affect operations. When problems occur, mission controllers must adjust, revising plans, troubleshooting issues, always aware that their commands will take minutes to reach Mars and that the rover must be able to handle problems autonomously if something happens between communication sessions. Despite these challenges, Perseverance maintains a remarkably productive pace. Over its first 3 years on Mars, the rover covered more than 17 miles, collected dozens of samples, made tens of thousands of scientific observations, and returned hundreds of thousands of images. It survived dust storms, temperature swings of more than 200 degrees between day and night, radiation from space, and the constant wear of driving over sharp rocks. The rover's longevity depends partly on clever engineering. Its wheels, for instance, are thicker and more durable than Curiosity's wheels, which suffered significant damage on the sharp rocks of Mount Sharp. Its drill bits can be replaced if they wear out, allowing the mission to continue even if one bit becomes dull. Its computer can reboot itself if it encounters a software problem, and redundant systems provide backup if critical components fail. But longevity also depends on the careful, conservative approach taken by mission controllers. They do not rush. They take time to study each rock before deciding whether to drill. They plan drives carefully, avoiding unnecessary risks. They test new techniques first, ensuring they are safe before relying on them regularly. This patience, this methodical approach, allows missions to last far beyond their original design life. Curiosity, Perseverance's predecessor, landed on Mars in August 2012 and is still operating more than 12 years later as of this writing. Spirit and Opportunity, earlier rovers, operated for years beyond their 90-sol design life, with Opportunity continuing for nearly 15 years until a massive dust storm finally ended its mission. These successes give mission planners confidence that Perseverance, too, can operate for many years, continuing to explore Jezero crater and collect samples for eventual return to Earth. As you settle deeper into rest, imagine the quiet dedication of the mission team. Picture them in darkened control rooms, studying data that arrived from Mars hours ago, planning tomorrow's activities, preparing commands to upload during the next communication window. They work in shifts, passing responsibility from one team to the next as Earth rotates and Mars grows distant or near in the sky. Their work is not glamorous. It is repetitive, meticulous, sometimes tedious. But it is also profound. Through their efforts, through their patient planning and careful commands, a robot on another planet explores a landscape no human has walked, studies rocks older than any civilization on Earth, searches for answers to questions that philosophers pondered long before science gave us the tools to investigate them. And Perseverance itself, tireless and patient, continues its work soul after soul, driving a bit farther, studying one more rock, drilling another sample, building slowly toward the moment when those samples might return to Earth and reveal secrets preserved in stone for billions of years. What has Perseverance discovered in its years of exploring Jezero Crater? The findings range from expected confirmations of what orbital studies suggested to surprising revelations that have reshaped our understanding of Mars' geological history. Each discovery adds a piece to the puzzle of Mars' past and helps answer the question of whether life might once have existed there. One of the earliest surprises came from the crater floor itself. Scientists had expected to find sedimentary rocks, deposits laid down at the bottom of the ancient lake that once filled Jezero. Instead, the rocks Perseverance first encountered were igneous, formed from cooling magma or lava. This was unexpected and required scientists to revise their understanding of Jezero's history. These igneous rocks showed evidence of interaction with water, however. Chemical analysis revealed the presence of carbonate and sulfate minerals, compounds that form when water alters rock chemistry. Some rocks contained olivine, a green mineral common in volcanic rocks, but also showed signs of weathering, suggesting water had seeped through the rocks long after they solidified. The most intriguing finding from these early studies was the detection of organic molecules. Organic molecules are compounds that contain carbon and hydrogen, often with other elements like oxygen, nitrogen, or sulfur. On Earth, most organic molecules are produced by living things, though some can form through non-biological processes. On Mars, organic molecules have been detected before, but their origin remains uncertain. Perseverance's Sherlock instrument, designed specifically to detect organic molecules, found them in several different rocks in Jezero Crater. Some were found in sedimentary rocks near the delta. Others appeared in igneous rocks on the crater floor. The molecules themselves are not direct evidence of life. They could have formed through geological processes, delivered by meteorites, or produced by chemical reactions between water and rock. But their presence is significant. Life as we know it requires organic molecules as building blocks. Finding them on Mars shows that the chemistry of life, the raw materials from which living things might form, existed on Mars. Whether those materials ever organized into living systems is still unknown, but at least the preconditions were present. As Perseverance drove westward across the crater floor toward the delta, it encountered a variety of rock types, each telling part of Mars' complex history. Some rocks were conglomerates, collections of rounded pebbles cemented together, indicating they had been transported and smoothed by flowing water. Others were fine-grained sandstones, suggesting deposition in calmer water. The rover also found rocks with nodules and veins, features that form when mineral-rich water flows through cracks and pores in rock, depositing minerals as the water evaporates or cools. These features are common in sedimentary rocks on Earth and indicate prolonged interaction between rock and water, exactly the kind of environment where life might have thrived if it existed on Mars. When Perseverance finally reached the base of the delta, mission scientists were thrilled. This was the primary target, the reason Jezero Crater had been chosen. The delta's sedimentary layers, clearly visible from orbit and now examined up close, provided a detailed record of water flow into the ancient lake. The rover climbed carefully up the delta's slope, its wheels gripping weathered sedimentary rock. At various points, Perseverance stopped to study outcrops, places where erosion had exposed layers of rock, allowing instruments to see the internal structure. These studies revealed fine layering, the kind produced when sediments settle in standing water layer upon layer over time. Some layers were rich in clay minerals, which form in calm water conditions. Others contained more coarse-grained sand, suggesting periods of faster water flow. The pattern of these layers told a story of environmental change, of times when the lake was deep and calm alternating with times when floods brought sediment rushing in. Perhaps the most exciting discovery came from a rock informally named Chiava Falls, located in a part of the delta called the Martian Unit. This rock, about 3 feet by 2 feet in size, contained several features that intrigued astrobiologists. First, Sherlock detected organic molecules in the rock. Second, the rock contained distinctive spots, roughly circular features a few millimeters across that resembled structures called leopard spots on certain rocks on Earth. On Earth, leopard spots can form when chemical reactions involving bacteria create localized changes in rock chemistry. The spots on Chiava Falls contained iron phosphate, a compound that, on Earth, is often associated with biological activity. But the spots could also have formed through purely geological processes. Without more detailed analysis than Perseverance's instruments can provide, the ambiguity cannot be resolved. Adding to the intrigue, the rock also contained veins of calcium sulfate, a mineral that forms from water running through it. And in those veins, arranged in rows like beads on a string, were tiny crystals of a mineral that should not be there given the rock's formation history. These crystals suggested that multiple episodes of water flow, at different times and under different conditions, had affected the rock. Mission scientists were careful not to overinterpret these findings. The features in Chiava Falls could be biosignatures, traces left by ancient microbial life. Or they could be abiotic, formed entirely through geological and chemical processes without life's involvement. The rock was deemed important enough that a sample was drilled and cached, ensuring that if it is ever brought to Earth, scientists will be able to study it with instruments far more sophisticated than anything that can be sent to Mars. This ambiguity is common in the search for ancient life. Life leaves traces, but so do many non-biological processes. Distinguishing between the two often requires multiple lines of evidence, detailed analysis, and careful comparison with known examples from Earth. For rocks billions of years old, from a planet with a very different geological history than Earth, making definitive determinations is extraordinarily challenging. Other discoveries have been less ambiguous but no less important. Perseverance has documented in detail the geological diversity of Jezero Crater, mapping different rock units, understanding their relationships, building a three-dimensional picture of the crater's layered history. The rover has found evidence of multiple episodes of water activity, some ancient, some more recent. It has found rocks altered by volcanic heat, rocks weathered by water, rocks eroded by wind. The mission has also characterized the Martian environment in unprecedented detail. META, the weather station, has recorded thousands of measurements of temperature, pressure, wind speed, and humidity. These data show that Mars has a dynamic atmosphere despite being thin. Dust devils are common, stirring up dust that hangs in the air for hours. Temperatures swing wildly, from relatively warm midday temperatures near freezing to bitterly cold nights well below -100 degrees Fahrenheit. Perseverance has captured sounds of Mars, adding an auditory dimension to our understanding. The recordings reveal a quieter world than Earth, where sounds are muffled by the thin atmosphere and travel more slowly, especially low-frequency sounds. The crack of the laser hitting rocks, the crunch of rover wheels on gravel, the whisper of wind, these sounds bring Mars closer, making it feel more real, more tangible. The mission has also documented seasonal changes. Mars has seasons because its axis is tilted similarly to Earth's, about 25 degrees. As Mars orbits the Sun, different hemispheres tilt toward or away from the sunlight. Perseverance has observed how frost forms in shadows during winter and how the atmospheric pressure changes as carbon dioxide freezes out of the atmosphere at the poles during their respective winters and then sublimates back into gas during spring. Perhaps one of the most important contributions of the mission, though, is simply the sheer volume and quality of data it has returned. Every image, every spectrum, every measurement adds to our knowledge. Mission scientists have published dozens of research papers based on Perseverance's findings, and hundreds more will follow as the data is analyzed in detail. Other researchers, not directly involved in the mission, can access this data and conduct their own studies, bringing fresh perspectives and new insights. This open approach to data sharing is a hallmark of modern planetary science. Data from Mars missions is archived and made publicly available, allowing scientists worldwide to contribute to the analysis. High school students have discovered new features in Mars images. Amateur scientists have created stunning panoramas from raw image data. The knowledge gained from Mars exploration belongs to all of humanity, shared freely so that we can all learn from what we discover. As you rest here, breathing slowly, drifting, think of those discoveries. Picture scientists on Earth examining images of rocks billions of years old, rocks that might contain traces of ancient life, or might just be interesting geology. Think of the conversations, the debates, the careful weighing of evidence. Science is not about certainty. It is about building understanding from evidence, revising ideas when new data demands it, always staying open to surprise. Mars continues to surprise us. Every mission reveals something unexpected, something that challenges our assumptions or forces us to think differently. Perseverance is no exception. The mission was designed to search for signs of ancient life, but in doing so, it has also taught us about volcanism on Mars, about how water shaped the landscape, about the planet's climate history, about dust and wind and the slow processes of erosion that continue today. The rocks Perseverance has cached, sitting in titanium tubes on the Martian surface or stored in the rover's belly, represent the best candidates we have yet found for answering the life question. They come from a place where water once flowed, where organic molecules are present, where conditions may have been suitable for life billions of years ago. If those rocks ever return to Earth, they will be studied with the intensity and thoroughness that only terrestrial laboratories can provide, examined atom by atom, molecule by molecule, for any hint of biology. The answer might be yes, life existed. Or it might be no, Mars was always sterile. Either answer would be profound. Either would teach us something fundamental about how life arises, how common or rare it is in the universe, whether Earth is a lonely oasis or just one living world among many. As of late 2024, Perseverance continues to operate, exploring the upper reaches of the delta, studying rocks that formed in the ancient lake's shallower waters. The rover has many miles still to travel, many rocks still to study, many samples yet to collect. Mission planners have outlined an ambitious traverse that will take Perseverance out of the crater entirely, climbing up onto the crater rim where even older rocks, dating from before the impact that created Jezero, might be exposed. This journey will take years. Mars exploration is not a sprint. It is a marathon, a patient accumulation of observations and measurements, a slow building of understanding. Every soul brings new data, new images, new discoveries. And every soul takes the mission closer to its ultimate goal, understanding whether life ever existed on Mars. The success of Perseverance has already influenced planning for future Mars missions. The techniques demonstrated by the mission, particularly terrain relative navigation for landing and the sample caching system, will be used by subsequent missions. Ingenuity's success has led to plans for more sophisticated aerial vehicles. MOXIE's demonstration of oxygen production has been incorporated into plans for eventual human missions. The most immediate successor to Perseverance is the Mars Sample Return Campaign, one of the most ambitious missions ever attempted by space agencies. Current plans, though subject to change as budget and technical considerations evolve, envision multiple launches in the late 2020s. A lander would carry a fetch rover or small helicopters to collect samples from Perseverance or from the Three Forks Depot. A Mars ascent vehicle would launch those samples into Mars orbit. An Earth return orbiter would capture the samples and bring them back to Earth. The timeline is long. Sample return is unlikely to occur before the early 2030s. But when it does, those samples will represent the first pristine rocks from Mars ever studied in terrestrial laboratories. Scientists will be able to use techniques impossible to deploy on Mars: ultra-high-resolution microscopy, isotope analysis that can determine precise ages, searches for complex organic molecules or minerals that require large laboratory equipment to detect. If biosignatures are present in those rocks, the sensitive instruments on Earth will find them. If fossils exist, even microscopic ones, they will be seen. If the rocks contain isotope ratios characteristic of biological processing, those ratios will be measured. The samples will likely be studied for decades, becoming some of the most thoroughly analyzed rocks in existence. Beyond sample return, NASA and other space agencies are planning the next generation of Mars missions. Concepts include drilling rovers that can access deeper layers of rock, potentially reaching meters beneath the surface where preservation of organic material might be better. Aerial vehicles like Dragonfly, headed to Titan, might inspire similar designs for Mars, capable of covering vast distances and accessing locations too steep or rough for wheeled rovers. There are also concepts for missions to search for extant life, life that might exist on Mars today. While the surface is hostile, with intense ultraviolet radiation, extreme temperature swings, and no liquid water, the subsurface might be more hospitable. If liquid water exists as groundwater a few kilometers down, kept liquid by Mars' internal heat, then life might persist there, protected from the harsh surface conditions. Detecting such life would require drilling deep beneath the surface, something no Mars mission has yet done. But technologies for deep drilling exist on Earth, and adapting them for Mars is technically feasible, if expensive and challenging. A mission to drill several kilometers into the Martian crust could potentially access these deeper water reserves and search for microbial life that might still flourish there. Looking further ahead, perhaps to the 2040s or beyond, lies the possibility of human exploration. Sending humans to Mars is a goal that has motivated space exploration for decades. The challenges are immense. The journey would take 6 to 9 months each way. Astronauts would be isolated and unable to return quickly if something went wrong. The radiation exposure during the journey in on the surface is significant, and the psychological strain of such a mission would be considerable. Yet the lessons learned from robotic missions like Perseverance help make human missions more feasible. We now know where water ice can be found on Mars. We know that oxygen can be produced from the atmosphere. We have detailed maps of potential landing sites and knowledge of what resources are available. We understand the dust, the radiation, the temperature extremes that astronauts would face. A human mission to Mars would likely land at Jezero Crater or a similar site chosen for its scientific interest and its resources. Astronauts would explore far more rapidly than rovers can, covering in days what takes rovers months. They could make judgment calls in the field, adjusting their plans as they discover new features. They could collect samples with care and discrimination that no robot can match. They might even visit Perseverance itself, a historical monument by that time, a relic of the robotic era of Mars exploration. They might examine the rover, perhaps perform maintenance if it were still operating, or simply pay their respects to the machine that blazed the trail they now follow. Human exploration of Mars would answer questions that robots cannot. It would push the boundaries of human endurance and capability. It would require international cooperation on a scale rarely seen. And it would represent a profound expansion of human presence beyond Earth, turning us from a single-planet species to a spacefaring civilization with a foothold on multiple worlds. But that future, exciting as it is, depends on the success of missions like Perseverance. We must first understand Mars with robots, learning how to operate there, what resources are available, what hazards exist. We must develop technologies for producing oxygen, for generating power, for protecting astronauts from radiation. We must test these technologies and prove they work in the real Martian environment, not just in simulations or vacuum chambers on Earth. Perseverance and its predecessors are scouts, pathfinders, preparing the way for those who might follow. Every discovery, every successful demonstration of new technology, every sample cached for future return, brings us closer to the day when humans might walk on Mars, look up at the pale sky, and know that they stand on a world their ancestors once glimpsed only as a red in the night. As you continue to relax, drifting deeper into rest, imagine that future. Not the technical details, not the challenges and difficulties, but the simple wonder of it, humans on Mars, exploring a world that has waited billions of years to be fully known. It is a future worth dreaming of, a future worth working toward, a future that begins with missions like Perseverance. We have traveled far tonight, from the launch pad at Cape Canaveral to the ancient crater floor where Perseverance now sits, from the early days of the mission to the discoveries and achievements that have marked its time on Mars. We have explored the instruments that give the rover its senses, watched Ingenuity take to the sky, discussed the ambitious goal of returning samples to Earth, and considered the future missions that will build on Perseverance's legacy. But perhaps the most important thing to take from this story is not the specific facts or achievements, impressive though they are. It is the broader meaning of what we are doing when we explore other worlds. It is about the human impulse to seek, to wonder, to reach beyond what is immediately knowable, to ask questions whose answers may take decades or centuries to find. Mars is not just a destination. It is a mirror held up to Earth, showing us what might have been and what could yet be. 4 billion years ago, Mars and Earth were not so different. Both had atmospheres, both had water, both had volcanic activity shaping their surfaces. Yet they diverged. Earth remained warm and wet, developing a rich biosphere that transformed the planet itself. Mars grew cold and dry, its atmosphere thinning, its water disappearing, leaving behind a silent desert world. Understanding why these two similar planets followed such different paths is not just academic curiosity. It teaches us about how planets evolve, about what conditions permit life to arise and persist, about what makes a world habitable. These lessons have implications for understanding Earth itself, for recognizing that our planet's habitability is not guaranteed forever, that climate and atmospheric conditions can change dramatically over geological time. Perseverance's mission, the search for ancient life on Mars, is also a search for perspective. If we find evidence that life once existed there, it would mean that life has arisen twice independently in our solar system alone. That would suggest life is not a rare accident but perhaps a common outcome wherever conditions permit. It would hint at a universe potentially teeming with life, at least in microbial form. If we find no evidence of life, despite Mars once having conditions that seem favorable, that too would be significant. It would suggest that the origin of life is more difficult, more improbable than we think. It would make Earth's biosphere appear more precious, more improbable, more deserving of protection and stewardship. Either answer changes how we see ourselves and our place in the universe. We are seekers of that answer, sending our robots across the solar system, gathering data, building understanding slowly and patiently. Perseverance is part of that quest, one explorer among many, but an important one, working at a location that offers some of the best prospects for finding the evidence we seek. The work continues, soul after soul, year after year. Perseverance will keep exploring Jezero Crater as long as its systems function, as long as its power holds, as long as there are new places to go and new rocks to study. The mission team will keep planning, commanding, analyzing data, publishing discoveries. The samples will wait, preserved in their tubes, for the day when they can return to Earth. And we, from our distant planet, can watch and learn. We can see through Perseverance's cameras the landscapes of another world. We can share in the excitement of discovery when something unexpected appears in the data. We can dream about what those sample tubes might contain and what they might reveal when they are finally opened in laboratories on Earth. This is the privilege of living in an age of exploration. Earlier generations could only wonder about Mars. They saw it as a point of light, speculated wildly about what might be there, wrote stories of Martian civilizations in canals. We have the privilege of knowing Mars as it really is, through the eyes of our robotic emissaries, through the data they send back, through the slow accumulation of knowledge that transforms mystery into understanding. Yet even as we learn, new mysteries emerge. Every answer prompts new questions. Every discovery reveals how much we still do not know. Mars still holds secrets. The universe still holds wonders. And we still have the curiosity, the drive, the will to explore them. As you lie here now, comfortable and relaxed, ready for sleep, let these thoughts drift gently through your mind. Think of perseverance on Mars, alone in a vast silence, working patiently under alien skies. Think of the people on Earth who built it, who operate it, who dedicate their careers to understanding what it finds. Think of the long arc of exploration, from ancient humans looking up at wandering stars to spacecraft that now traverse the solar system. We are all part of this story. We are all beneficiaries of the knowledge gained. We all share in the wonder of looking at images from Mars and knowing that this is real, that we as a species have achieved this, that we can do such things. Let that wonder be the last thought you take into sleep. Not wonder that demands answers or action, but simple wonder at what exists, at the beauty of a rust-colored planet circling the sun, at the ingenuity of a small rover exploring its surface, at the patient accumulation of knowledge that slowly answers ancient questions. Perseverance will be there tomorrow, and the day after, working quietly, exploring patiently, sending back its findings to Earth. The mission continues. The exploration continues. The search for understanding continues. And so we rest, knowing that while we sleep, somewhere millions of miles away, a rover sits on the surface of Mars, beneath a sky filled with stars that include our own pale blue dot, carrying forward humanity's dream of exploring the cosmos, one small drive, one careful measurement, one precious sample at a time. May your dreams be filled with the quiet wonder of distant worlds. And when you wake, perhaps you will look at the night sky a little differently, knowing that up there, among the stars and planets, our machines are exploring, our questions are being answered, and our understanding of the universe continues to grow. Good night.